Again, we don't have to get into the details of like what the heads are or layers. And then so you're basically saying the final output that you care about, which of these individual nodes give values that are closest to it. Okay, so you want to know who's doing interesting things. So you can see here on layer 9, head 8 again, just node 9 on layer 9. For example, this layer aligns very closely with some desired output. Okay, it doesn't matter what the output in question is. This could be like any problem, but like it's just like a crude, naive way of saying which of these nodes is voting highly for the thing that is correct. So like which of these nodes is like solving the problem. Again, if you simplify the model as being like if it's like checking with every node on what their vote is for the problem. Okay. But you will notice that there is an issue here, that the layers that have like colors lighting up here are very late. So like the other layers don't have anything going on. And the reason that is because it's a very like crude measure of what's happening. So the other layers aren't necessarily voting for the final problem. They're not all saying prime or non-prime. They might be doing something else, like maybe one of them is checking, is this number even or not? So this isn't exactly the problem we're solving, but it could be useful for the final result. So it's not very fair to just assume all these layers are useless because they don't align with the final result. But again, this is a great place to start because we just like, okay, at least which of these nodes, is like the final bottleneck for what is useful. So a method that like tries to look beyond just the obvious, that's like which nodes are explicitly voting prime or no prime, is activation patching. And what this is, again, this requires no understanding of LLMs, but just like at a high level, any arbitrary system that's a computational graph, you want to like study things about it, it's a black box, right? So what this method does is, we don't have to get too deep into the details, but basically, it allows most of the system to run normally with like the input you have, but then it picks on one of the nodes and it makes it run with a different input. So basically, like if you want to know, like all these, like how, I guess another like way this is slightly different from traditional software is like not everything here has to be useful for each problem, right? The neural network has a lot of problems it's trying to solve and uses different things to do that. The question is, we want to know which of these nodes is critical, like on the critical path to results. So like one way to do it is like imagine if you just like pick on one of these and you fiddle with them, just make them like random. The question is, you want to know if I mess with this node, does the output change? That's one way of making it on the critical path. Because if the output is like invariant to like any perturbation like disturbances, nothing will change, right? So let me just give you like one concrete example of what that looks like. If you have a network that is able to guess the result of this, okay? Which I guess like any GPT can easily do this, but when Mary and John went to the store, John gave the drink to. So this problem in like English grammar is not like a CS problem. It's called like indirect object identification. That is like, it's guessing the other object here, which is most likely going to be Mary. Okay? And I guess the anti-example of this is, if you flip it, you simply just say when Mary and John went to the store, Mary gave the drink to John. Cool. So,
I didn't get that.
okay, let me say that again. So this example, right? When Mary and John went to the store, John gave the drink to. The answer is most likely Mary, right? It's just for like, we can intuit that John is going to give it to. I mean, sure, John gave it to someone else, but like, just taking this in context, Mary is going to be more likely than John. Great. So the anti-example of this is the example where like just one thing is different, but it flips the order, right? So now John is way more likely than Mary in this other example. So I guess looking back to this, what we want to do is, okay, we want to know which of the components of the computational graph are critical for predicting Mary in the first example. So what we can do is we can pick on every single one and give them an input that is actually the anti-example. That is, we give them the second one, which is Mary. And then we judge if the output continues to be Mary or John. So once we find the input that, the node in this graph, that if we flipped it to the anti-example, the final result is that of the has flipped as well, then we know that, okay, cool, this node is very important because it's able to, just by flipping that example alone, the rest of the graph just changes the final output, right? This is, again, just another high-level, systems level, it has nothing to do with ML, just systems level, like, principled way of, like, finding which components are important to, like, put more focus on. Okay. And the third on the list is just basically staring at the attention patterns. Okay, now, to be fair, this is the first method that does depend on some familiarity with transformer networks and attention patterns, okay? But it's probably the most interactive or easiest to do, so I just have a little demo here, okay? So what basically happens is, again, in the big network, each node is specializing for something different. And sometimes just by giving it an input and staring at how the attention, again, I'll describe what attention is very shortly. But just by staring at how the attention patterns work, we can obviously just see what this node is trying to do. Right, and again, quick primer on attention. It's basically the feature of most state-of-the-art models that allow a given, so again, if you have an input, you want each token to, each of the, again, so this sentence here is made up of different tokens. So attention is what allows a given token to to get information from other tokens, okay? Again, details aren't that important, but this is just a way of showing how each different, again, all these boxes here are simply just different nodes. Okay, so now we want to look at what is happening inside of the nodes. This is what we're doing here. So each of these boxes is how the boxes are, how the nodes are responding to the input that we gave. So let me just cherry pick some good looking ones. So this particular one here, so if you notice as I hover around, so the direction is from, when the model is unnoted, it's going to pay attention to the thing that comes after the last occurrence of noted. Okay? So this is simply just called an induction head. It's a node that specializes on remembering the last time you saw something. Okay, so if you saw A, B, dot, and it sees A again, it just guesses that B is most likely going to come next. That's his job, he specializes. And you can obviously see he's literally doing that because, again, this example is simply just one text copied and pasted twice. So it really highlights what this model is, what this node is doing, this head is doing. Yeah, so basically if I hover over anything, the thing that is highlighted is what comes after the last time it saw the thing. This is what the model is doing. Okay. So what do results look like? So if you have a bunch of these tools that you're using them to discover little interesting things, what does a complete end-to-end example result look like of understanding what the model is doing to solve the problem? So I have some screenshots here. Again, not important to get into any of the details, but basically, this is what it looks like. It just looks like a schematic of, so again, for each of the different components, we drill in using some of those tools we saw and more to understand, okay, this different node here is copying data from another node to do this, and then layer by layer, we form a narrative that again is backed by experimental results to show that for sure, we know that this is how this model is able to do the interesting thing. Which again brings us back to what the goal is. That is, again, we want to build algorithms, we want to have a conceptual understanding of what the model is doing. So that, I guess that's why that makes sense that the results will look like this. So it's not quite it's not a formula, it's not a, if you want a formula, we already have the weights of the matrix, right? So what we want is a high level understanding, and this is what it looks like. It's just a schematic. But the schematic was derived from principles of investigation of what each thing is doing. This is another example of a schematic. I think I like this one because next to it shows, so for each layer there, you have, this obviously is an informal version of this, right? Most of the time, they publish papers to show what the results are, but this is just the first pass at understanding what the model is doing. So for each component of the transformer network, there is a whole horizon. Okay, here are the experiments we did, here are the results, here are the evidence, and we're sure that for sure this is what's happening. Because again, we can't really know, it's more akin to biology than physics. So we don't know for sure. We just have statistical evidence that this head seems to be doing this thing, or this component is doing this thing often. And it's the best we can do right now with like understanding what the models are doing. Cool. So that's what results look like. Let me just pause for either take questions now or like after.
Anytime you want.
Okay. Let me just pause. Breather. Or any questions, thoughts, or feedback on my speaking speed again. Yeah.
So I was just curious about what method is used at the final layers to convert the different modes of the nodes to an actual output.
Mm-hmm.
Does that play a part in trying to work backwards?
Yeah. Yeah, so just repeat the question is what is the method of like using the analogy of like votes being given, like how do we get the final output? So it's literally just addition. So like each component, again it depends on like the component in question, but for attention heads, the output is like a vector of numbers, and then you just literally add them to each other. So like to like determine which probability outcome is most likely. So the nodes that speak the loudest usually end up winning, right? So it's like, again, it's the output of each head at the end is like a probability distribution, on like which token comes next. So sometimes, if a node is really sure that this looks like the problem I'm meant to solve, the output will be very high there. And then, just like by vector addition, you just, the biggest thing wins. So yeah, just addition is really. Yeah. Alright, if no questions, yeah, just like some examples of how Mechanistic has been used like in industry for not just safety, but for actually like making improvements to performance. So this is a bit of like an anti-example because, and I'll explain shortly. So basically, and also I ignore all of this. If I could have, I would remove them, but like this is just a screenshot from the paper, so I couldn't help but add this, but it's not really important. What's important is this. So basically, the entire network of neural network is a bunch of matrix multiplications happening. Like again, bunch of big numbers, multiple big numbers, and so forth. And this again is of course expensive. But it turns out that a team discovered that some of the columns of these matrices are consistently like much larger. So they don't need to use the full 16-bit resolution of multiplications. They could instead just identify the columns that are usually larger, have those be 16-bit operations, and reduce the resolution of the other numbers. And of course, this will speed up performance. So what does this have to do with Mechanistic? It turns out that before this paper got released, there was a different Mechanistic paper that discussed the idea of whether we expect different columns to be bigger on average. And they said they didn't. So this paper actually disproved what that paper predicted. But after this paper got released, the Mechanistic team came back and gave an explanation of why that's the case. But the point though is that it's just the nature of the field to look at questions like this, like fundamental questions like, do we expect the numbers in this network to be consistently larger on one column or the other? And there's really no other subfield of research that is thinking this fundamentally on it. That's why I said this is an anti-example, because the perfect case is that the Mechanistic team discovered this and then they used to make a breakthrough. On the other hand, the Mechanistic predicted something different, and then another set of researchers found that they could find a performance improvement. But anyway, so any questions on why this is like what this breakthrough means, or is everyone clear on what it means? The idea of some columns constantly being larger at the end. Because again, if you just take a breather. We can all appreciate how 8-bit operations are less expensive to do than 16-bit operations, right? They have much larger numbers, great. So they found that consistently in a given transformer, there are some columns that do not need to be in 16-bit resolution, right? So hence that gave them an opportunity for a performance improvement. And again, this type of insight is in the ballpark of Mechanistic. So these are some of the benefits you are going to see outside of just safety in studying the models at a more intimate level. I think that's really most of it. So if anyone's interested in getting started with this, here are some resources. This is really great. A lot of the slides, the screenshots of the notes came from this course, Arena of Education, and the Anthropic team has published a lot of papers as well in the foundational model of the industry. And Neil, so can we share the slides after? So So don't worry, you get all this as well. And for concerns with like math, you honestly just mostly need linear algebra and I guess some statistics to get going. Calculus is just whatever calculation you need to understand ML. But for the field in particular, linear algebra, I guess, is quite important to have a good time. But yeah, that's all. Thanks. Don't have questions.